Today, we're going to talk about classes, one of the core building blocks of object-oriented programming, and we'll look at how classes are implemented and used in both Java and Python. You can think of a class as a blueprint or a template. Just like the star-shaped mold on the slide, a class defines the shape and structure of something, but it's not the thing itself. The actual objects we create, called instances, are like the finished soaps. They all share the same structure, but each instance can have its own data and behavior. Java and Python both support object-oriented programming, but they approach it a little differently. Java is more explicit and strict, while Python is more flexible and concise. Understanding both will help you recognize the common concepts that apply across programming languages. By the end of today's lecture, you should be comfortable reading and writing simple classes in both languages, creating objects from those classes, and understanding how data and behavior are bundled together. Before we go deeper into classes, we need to talk about methods, which are also commonly called functions. A method is simply a named sequence of instructions. Instead of writing the same steps over and over again, we package those steps into a single unit and give it a meaningful name. This idea of packaging is important. When we put multiple steps into a method, we make our code easier to understand, reuse, and maintain. Think about it this way. When you see a method call, you don't need to know every line inside it immediately. The name of the method tells you what it does and the details are hidden inside. A function group's behavior, it tells the computer how to do something. But real-world problems don't just have behavior. They also have data that needs to be stored, updated, and protected. That's where classes come in. A class groups data and behavior together. Instead of having data floating around in variables and behavior scattered across functions, a class keeps everything related in one place. For example, a student class might store a student's name, an ID, but its methods might calculate GPA, print a transcript, or update enrollment information. A student class isn't just a set of functions, and it's not just a collection of variables. A student has data, like name and ID, and behavior, like enrolling in a class or calculating GPA. When we create objects from a class, each object carries its own data and knows how to operate on that data using its methods. This approach scales much better as programs grow. When systems get large, managing dozens of global variables and standalone functions becomes difficult and error-prone. Objects help us manage complexity. They let us break a large system into smaller, self-contained pieces that are easier to understand, test, and maintain. That's why modern software, from games to mobile apps to large enterprise systems, is built around objects and classes. What you're looking at here is a blueprint of a starship. It shows structure, components, and how everything fits together. But this blueprint is not the ship itself. In programming terms, this blueprint is like a class. A class defines what something looks like and what it can do. It specifies the parts, data, and the operations, methods. But it doesn't actually exist in the real world yet. The real ship, the one flying through space, that's an object or an instance of the class. You can build multiple ships from the same blueprint. Each ship follows the same design, but each one is a separate object with its own state. This is exactly how classes work in Java and Python. A class defines the structure once, and then we can create many objects from it. Each object has the same methods but its own data. One ship might be docked, another might be in warp. Same class, different state. This is why classes are so powerful. They let us model complex systems in a clean, organized way without rewriting code over and over again. As we move forward, keep this picture in mind. Class equals blueprint. Object equals the real thing built from that blueprint. Now let's formalize some of the key terms we've been using. At the center of object-oriented programming is the idea of a class. A class is a blueprint or a template. It describes what something is made of and what it can do, but it is not a real thing by itself. Inside a class, we define two main components. First are attributes. Attributes represent the data, the information we want to store. For example, a student's name, ID number, or GPA. Second are behaviors, which are implemented using methods. Behaviors describe the actions an object can perform, such as enrolling in a class or calculating a GPA. So when you look at a class definition, you should always be asking, what data does this object store and what behaviors does it support? Once we have a class, we can create an instance, which is also called an object. An instance is a real, concrete version of the class. It follows the blueprint, but it has its own specific data values. For example, you might have one student class but many student objects, each with a different name and ID, all using the same methods. This distinction is extremely important. The class defines the structure. The object is the actual thing you work with in your program. Next, we'll see how this looks in actual Python code. Now let's look at a very simple Python class example. On line 1, we define a class named sample. This is the blueprint. We're not creating an object yet. We're just defining what the class looks like. Inside the class, on line 2, we define a method called display. This method contains behavior. In this case, it simply prints a message. On line 3, the print statement is the actual work being done by the method. Then on line 5, we call sample.display. Notice something important here. We are calling the method directly from the class, not from an object. This works in Python because methods are essentially functions stored inside a class. At this point, we are focusing on structure, not yet on objects or instances. This example is intentionally simple so we can focus on how a class and a method are defined before we introduce more details. We'll improve this example by creating an instance of the class and by introducing the self parameter, which allows methods to work with object-specific data. Now let's look at a more realistic Python class example. On line 1, we again define a class named sample. This is still just the blueprint. On line 2, we see a special method called underbar init underbar. This is the constructor. The constructor runs automatically every time we create a new object from the class. Notice the first parameter, self. In Python, self refers to the current object being created. The second parameter, age, is a value passed in when we create the object. On line 3, we assign self.age equals age. This creates an instance variable named age that belongs to this specific object. Every object created from this class will have its own age value stored inside it. Next, on line 5, we define another method called display. Again, notice that self is the first parameter. This allows the method to access the object's data. On line 6, we print the value of self.age. This shows how a method can use an instance variable. On line 8, we create an object by calling sample25. This line does two things. It creates a new object, and it calls the constructor with age set to 25. Finally, on line 9, we call obj.display, which prints the age stored in that object. This is the core idea of object-oriented programming in Python. Data lives inside objects, and methods operate on that data. Let's lock in the basic syntax rules for writing classes in Python. First, class names use camel case. This is a convention, not a rule enforced by the language, but it's extremely important for readability and professionalism. Second, methods are defined inside the class using the def keyword. Indentation matters in Python. Everything that belongs to the class must be indented under the class definition. Third, and most importantly, self refers to the current object. Anytime you want to store data inside an object or access that data later, you must use self. In the code example at the bottom, notice the overall structure. we start with class name. This defines the blueprint. Inside the class, we define the constructor using init. This method runs automatically when an object is created. Inside the constructor, self.attribute equals value creates an instance variable that belongs to the object. Every object created from this class will have its own copy of that attribute. If you forget self, Python will not know whether you're referring to a local variable or an object's data, and your code will either fail or behave incorrectly. These rules may feel small, but they form the foundation of every object-oriented program you'll write in Python. Let's look at an example. Here we define a student class. The constructor takes a name and a student ID, and it also initializes credits to 0. Every time we create a student object, the init method runs and sets up that object's data. On line 7, we create our first object, S1, and send in Alice and V 0010000. On line 8, we create a second object, S2, and send in Bob and V001000101. Even though both objects come from the same class, they are completely separate objects in memory. Each object has its own copy of the attributes. S1 has its own name, ID, and credits, and S2 has its own name, ID, and credits. When we print S1.name, we get Alice. When we print S2.student_ID, we get Bob's ID. This is the key idea. A class defines the structure, but each object stores its own data. You can think of the class as a form, and each object as a filled-out copy of that form. We're still using the same student class, but this time we added one more method, add credits. Notice that, like the constructor, add credits has self as its first parameter. This tells Python that the method belongs to an object and that it can access and modify that object's data. Inside add credits, we update self.credits by adding the given amount. This is important. The method is not changing a global variable. It's changing the state of one specific object. On line 10, we create a student object named S1. On line 11, we call S1.addCredits3. When this method runs, only S1.credits is updated. Finally, when we print S1.credits, we see the updated value, 3. Now let's look at a very common mistake when writing classes in Python. At first glance, this code might look reasonable. We define a counter class, and inside the constructor, we set count equals 0. But this code is wrong. The problem is that count is just a local variable inside the init method. As soon as the constructor finishes running, the variable count disappears. That means the object does not actually have a count attribute. On line 7, we create an object using obj equals counter. At this point, the constructor runs, but it does not attach count to the object. Then on line 8, we try to access obj.count. Python now looks inside the object for an attribute named count. It doesn't find one. So Python raises an attribute error, meaning this object does not have an attribute called count. This error is one of the most common errors you'll see when working with classes in Python. The key lesson here is very simple but very important. If you want a variable to belong to an object, you must use self.variableName. Without self, the variable lives only inside the method and disappears when the method ends. In the next slide, we'll fix this class by correctly defining self.count, and the error will go away. This version of the counter class is written correctly. On line 2, we define the constructor init just like before. But on line 3, notice the key difference. We use self.count equals 0. This attaches the variable count directly to the object. Now count is an instance variable, and it belongs to every counter object we create. On line 5, we create an object using obj equals counter. When the constructor runs, self.count is created and initialized to 0. On line 6, when we print obj.count, Python finds the attribute and prints the value. This time there is no error, and the output is 0. The only change between the wrong version and the correct version is the use of self, but that one change makes all the difference. Whenever you see an attribute error in Python, one of the first things you should check is whether you forgot to use self when defining an instance variable. Now let's talk about an important distinction in object-oriented programming: instance attributes versus class attributes. First, an instance attribute belongs to one specific object. When we create an instance attribute using self.variableName, that variable is stored inside that particular object. If we have two objects, each object gets its own copy of the instance attribute, and changing one does not affect the other. Second, a class attribute belongs to the class itself, not to any single object. That means a class attribute is shared by all objects created from that class. Every object can access it, and if it changes, the change is visible to all objects. This difference is extremely important because using the wrong type of attribute can lead to subtle bugs. A good rule of thumb is this: if the data describes an individual object, it should be an instance attribute. If the data describes something common to all objects, it should be a class attribute. Here we define a class called bank account. On line 2, notice the variable interest rate equals 0.02. This variable is defined outside of the constructor and inside the class. That makes interest rate a class attribute. There is exactly one interest rate, and it is shared by all bank account objects. Next, in the constructor, we define owner and balance using self. These are instance attributes. Each account has its own owner and balance. So if we create two bank accounts, they may have different owners and balances, but they will both use the same interest rate. This makes sense conceptually. The interest rate is a property of the bank, not of an individual account. If the bank changes the interest rate, that change should apply to all accounts. This slide shows one of the most dangerous and subtle bugs you can write in Python classes. At first glance, this class looks fine. We define a class called bad, and we create a list called items. The problem is where that list is defined. Items is a class attribute, not an instance attribute. That means there is only one list, and it is shared by all objects created from this class. Now watch what happens. We create obj1 with the value 1, and then we create obj2 with the value 2. Both constructors append their values to the same list. So when we call obj1.printItems and obj2.printItems, they both print the exact same contents. This is almost never what you want, and it leads to bugs that are very hard to track down. Let's switch gears and look at how the same ideas appear in Java. In Java, everything is object-oriented, and all code lives inside classes. Even when you write a simple Hello World program, Java still requires you to define a class. Here, we are defining a class named sample. In Java, there is no top-level code like in Python. All executable code must live inside a class. Notice the keyword public. This is an access modifier, which controls where the class can be accessed. We'll come back to access modifiers later. Inside the class, we see the main method. Public static void main string array, ARGS, is the entry point of a Java program. The name ARGS stands for arguments, which are values that can be passed into the program when it starts. We'll come back to this later. When a Java program runs, execution always begins in the main method. The system.out.println statement prints output to the console, similar to print in Python. Even in this simple example, we can already see an important difference. Java is more explicit and structured than Python. However, the core idea is the same in both languages. A class is a container that groups code together. What you're looking at here is a method. In object-oriented programming, we often describe methods as behavior. They define what a class or object can do. You may also hear the terms method and function used interchangeably. In Java, we typically say method when a function belongs to a class. So when we say class method or method, we're talking about a function that lives inside a class. Here, main is a method that defines the behavior of the sample class. This particular method is special because it is marked static, which means it belongs to the class itself, not to any specific object. That's why Java can run this method without first creating an object. Inside the method body, we see the actual instructions, the behavior, executed when the method runs. So conceptually, the class groups related code, methods define behavior, and this behavior runs when the method is called. In Python, reading user input is very simple. We just use the input function. In Java, reading user input requires more setup because Java is more explicit about how input is handled. The first thing we must do is import the scanner class. Scanner lives in the java.util package, so we write import java.util.scanner at the top of the file. This tells Java that we plan to use the scanner class in our program. In Java, input is handled through objects, not built-in functions like in Python. That means we must create a scanner object before we can read anything from the user. We then create an object using the new keyword. This is very different from Python's input function. After creating the scanner object, we store it in a variable. Here, we store it in a variable named scnr. So in Java, user input is handled through objects, and we interact with those objects by calling methods. In this example, on the last line, we invoke the nextant method that belongs to the scanner object. Scanner.nextant reads the next integer typed by the user and returns that value. We then store the return value in an integer variable called hourly wage. Let's look at this example and think carefully about what's happening. Here, we're trying to store information about multiple students. Using the concepts we learned before introducing objects and classes, the most intuitive approach is to use multiple arrays to store the data. So we create 3 separate arrays. The name array stores student names. The average array stores each student's numeric average. And the grade array stores each student's letter grade. All 3 arrays use the same index to represent the same student. For example, index 0 in all 3 arrays refers to the same student. Name 0, average 0, and grade 0 all belong together. This approach is known as parallel arrays. The diagram at the bottom illustrates this visually. Each column is a different array, and each row represents a single student. While this approach works, it has some serious drawbacks. First, the relationship between the data is implicit, not explicit. There's nothing in the code that guarantees name 2 actually belongs with average 2 and grade 2. We just have to remember that. Second, this approach becomes difficult to manage as programs grow. If we want to add more information, such as student ID, major, or credits, we have to add more arrays and keep all of them perfectly synchronized. This is exactly the kind of problem that classes and objects are designed to solve. Instead of spreading related data across multiple arrays, we can group everything that belongs to a student into a single student object. Now let's look at the same student information represented in a different way. Instead of using multiple arrays, we define a student class. This class groups all data that belongs to a student into a single unit. Inside the student class, we define 3 attributes. Name stores the student's name. Average stores the student's numeric average. And grade stores the student's letter grade. The important difference here is that these values are no longer spread across separate arrays. Each student object contains its own name, average, and grade. That means the relationship between the data is now explicit, not implicit. We no longer have to rely on matching array indices to keep information aligned. If we want to add more information, such as student ID, major, or credits, we simply add new attributes to the class. This makes the code easier to read, easier to maintain, and much less error-prone. This is one of the core benefits of object-oriented programming. grouping related data into meaningful objects. It's not just attributes or variables that we can group together. We can also group behavior. Object-oriented programming isn't only about storing data, it's also about defining what an object can do. In the bottom section of the class, we define methods, which represent behavior. PrintName is a method that prints the student's name. PrintAverage prints the student's numeric average. And PrintGrade prints the student's letter grade. What's important here is that each method operates on the data that belongs to the same object. That means a student object doesn't just have data, it also knows how to work with that data. This keeps related data and behavior together in one place. If we ever want to change how student information is displayed, we only need to update the methods inside the class. This design makes the code easier to understand, easier to modify, and less likely to break. This is the core idea behind classes. Objects represent real-world entities with both data and behavior. A class is a programmer-defined data type. It allows us to group related variables, which store data, and methods, which define behavior. In other words, a class bundles data and the operations that work on that data into a single unit. This is what makes programs easier to organize, understand, and maintain. A method is a named list of statements. When we refer to a method by its name, those statements are executed. A method may also return a value back to the caller. Calling a method is referred to as a method call. Any value we pass into a method is called an argument. Methods allow us to organize code, reuse logic, and define behavior. So we already know that one way to use a class is to create an instance and then use that object. For example, when we use scanner, we create a scanner object and then call methods on that object. There is another way to use classes. In Java, we can also use class methods, also called static methods, without creating an object. For example, math.square-root-5 calls a method directly on the math class. There is no math object being created here. This works because square root is a static method, meaning it belongs to the class itself, not to any instance. So why do we use static methods? We use static methods when the behavior does not depend on any specific object's data. Methods like square root, power, or absolute value perform general calculations. They don't need to remember or store state. Making these methods static avoids unnecessary object creation and makes the code simpler and clearer. So Java supports two usage patterns: instance methods that operate on object data and static methods that provide general-purpose behavior. Let's look at this example. Here we define a simple Java class named callee. Inside this class, we define a method called printMyName. This method prints a string to the console. Notice that this method is not static. That means printMyName is an instance method, as you can see here. Instance methods belong to an object, not to the class itself. So in order to call this method, we must first create an object of the callee class. Once we have an object, we can call printMyName using that object. Now let's look at this example carefully. We have a class called caller with a main method. Inside main, we try to call callee.printMyName. This line is highlighted because it is incorrect. The problem is that printMyName is an instance method, not a static method. Instance methods belong to objects, not to the class itself. But here we are trying to call the method directly on the class name callee. Java does not allow this. To call an instance method, we must first create an object of the callee class. Only then can we call printMyName using that object. Java immediately tells us that something is wrong when we try to run this code. The last line of the message shows exactly where the problem occurred. Caller.java, line 8. This error reinforces an important rule in Java. Static code cannot directly call non-static methods without an object. Now let's fix the problem by changing the method. Here, printMyName is declared as static. That means this method now belongs to the class itself, not to any specific object. Because the method is now static, we no longer need to create a callee object to call it. Static methods can be called directly using the class name. So calling callee.printMyName is now valid and will work correctly. This is exactly how methods like math.squareRoot work. So remember this. If a method does not depend on object-specific data, making it static can be appropriate. This slide shows the general structure of a method in Java. Every method must be defined inside a class, between the opening and closing braces. A method definition includes 4 main parts: an optional modifier like static, a return type, a method name, and a list of parameters. The method name must be a valid identifier. The parameter list specifies what values must be passed into the method. The return type indicates what kind of value the method sends back. Inside the braces, the method contains local variable declarations and statements that define its behavior. This structure is the same for all methods you will write in Java. This slide shows the general form of a method call in Java. To call a method, we write the method name followed by parentheses. Inside the parentheses, we place the argument list. The argument list is a comma-separated list of values or expressions. The types of these arguments must match the method's parameter definitions. If a method has no parameters, the argument list is empty, but the parentheses are still required. When a method is called, it executes its code and returns a value. Because of that, a method call can be used inside a larger expression. This syntax applies to all method calls you will write in Java. This example shows the correct way to call an instance method in Java. PrintName is an instance method, so it belongs to an object. Because main is static, we must first create an object. We create a test object and store it in T. Then we call the method using the object, t.printName. This is the standard pattern for calling instance methods in Java. This code will not compile. PrintName is an instance method, but main is static. Static methods cannot directly call non-static methods. There is no object here, so Java doesn't know which instance to use. To fix this, we must either create an object or make PrintName static. PrintName is now a static method, so it can be called directly from main. No object is needed. Each call to PrintName executes the same code, so the message is printed twice. There are 3 main reasons we define methods. First, methods improve readability. When main calls high-level methods, the program is easier to read and understand. Second, methods support modular program development. Each method has a clear input and output, so we can develop and test pieces of the program independently. Third, methods help us avoid writing redundant code. We define a method once and reuse it wherever we need it, instead of rewriting the same logic over and over. These ideas apply to both Java and Python, and they are fundamental to good program design. Here is a sample exam question. And the answer is 6. The printFace method contains 3 output statements. In main, we call printFace twice. Each call runs all 3 statements, so a total of 6 output statements execute. This is another question. And this time the answer is 3. Here are the key terminology you need to remember. We have a class, which is the outer structure. Inside the class, we define a method. Inside main, we make a method call. Int here is the return type. It tells us what the method sends back. Inside the parentheses, int first and int second form the parameter list. When we call the method, num1 and num2 are the arguments. Remember this distinction. Parameters are in the method definition. Arguments are in the method call. Let's do a quick true or false check. First, a parameter may be an expression. This is false. Parameters are variables defined in the method header. Second, An argument may be an expression. This is true. Arguments can be values, variables, or expressions like x plus 1. Third, a method may have multiple parameters. True. Fourth, a method may have multiple return values. False. And finally, a method must return a value. False. Methods with return type void do not return a value. Before we wrap up, I want to emphasize something important. This lecture covers the most essential concepts related to classes, objects, and methods. However, it is not comprehensive. To fully understand classes and objects, you must read the chapter on classes in the textbook. The lecture is meant to guide you and highlight key ideas, but the textbook provides the full details, examples, and edge cases.
This lecture was prepared by June Lee with the assistance of AI Technologies. See you next time!